one of the very important aspects of chemical equilibrium is change in temperature. This we are discussing separately because temperature also affects the equilibrium, but in not same manner like change in pressure or volume or number of moles too. Up to now we have seen if we change number of moles or volume or pressure, then equilibrium adjusts itself in order to bring it back to the same ratio, same equilibrium constant. Change of temperature affects the equilibrium in totally a different manner. How? That in this case, the equilibrium constant itself changes. Take one example. PCl5, if we take, this gives PCl3 and Cl2. This is a thermal decomposition reaction, and the forward reaction is endothermic. Means we have to heat it in order to obtain PCl3 and Cl2. So forward reaction is an endothermic reaction, and one thing is for sure that if forward is endothermic, backward will be exothermic, and vice versa. Means if forward is exo, then this is 100% sure backward will be endothermic. Right? Now, what Lee-Childress says, theoretical principle if we discuss about, simply Lee-Childress theoretical principle says that if you increase temperature, equilibrium shifts in that direction where the reaction is endothermic. Means in this particular case, if we give it temperature, means if we heat it, if we give it energy, then equilibrium is going to shift in forward direction. More of PCl5 will decompose to produce PCl3 and Cl2. Similarly, if you decrease the temperature, means we are extracting the heat from the system, then equilibrium shifts in that direction where the reaction is exothermic. Means in this particular case, reaction is going to shift in backward direction. Right? Now, if we go for mathematical explanation for this, we have to go somewhat way back for writing Arrhenius equation, and Arrhenius equation says that rate constant Kf for forward reaction, if I am writing it, rate constant of the forward reaction Kf is given as equal to AF, Arrhenius constant for the forward reaction, into E to power minus EAF, which is activation energy of forward reaction, by RT. Similarly, if I write rate constant for backward reaction in terms of Arrhenius equation, this becomes Kb equal to AB into E to power minus EAB by RT. Now, as we have seen, equilibrium constant is nothing but ratio of Kf by Kb. So, this we divide these two equations, we get this one here. Right? This is nothing but equilibrium constant at temperature T. I am writing as Kt. Okay. Now, this will be equal to Kf by Kb, Af by Ab, E to power minus Af by RT, E to power minus Ab by RT. This is Ef, this is Eab. Activation energy of backward reaction, activation energy of forward reaction. Suppose we change temperature now. This we assume to be temperature T1. So, this becomes equilibrium constant at temperature T1 here. Arrhenius constants and activation energies are assumed to be constant in the given temperature range. So, you are not going to put 1 or 2 on them because they will be same for second temperature range also. Similar equation we write for the forward and backward rate constants for temperature T2. Now, Kf2, we assume this one to be Kf1 and Kb1. Kf2 in similar manner will be equal to Af. Remember, I told you Rn is constant and activation energies are remains constant. We assume to be them constant. It becomes Af e to power minus Ef by RT2. Kf2, this is, now we get Kb2, which will be equal to Ab e to power minus Eab by RT2, right? Again, this ratio will be equal to KT2, which is equilibrium constant at temperature T2. This one here. We divide KT2 by KT1. Then we get KT2 by KT1. As you can understand that AF, AB will get cancelled, right? And we get here in terms of EAB and EAF, right? So we get here KT2 by KT1 equal to e to power EAB minus EAF upon T1 minus T2, right? We take minus log, this will come with minus sign. We put minus log on both sides, sorry, log we put on both sides, so it becomes log KT2 by KT1 equal to, this becomes EAF minus EAB upon 2.303, right, and into 1 by T1 minus 1 by T2 here. Right up now? Clear? Now, this I also comes here, EAB minus EAF upon T1 minus T2, this will be here 1 by R into 1 by R here. Okay, so upon 2.303 R, log K2, KT2 by KT1 equal to EAF minus EAB upon 2.33 R 1 by T1 minus 1 by T2. This becomes equal to delta H upon 2.303 R into 1 by T1 minus 1 by T2, right? This is how we get equilibrium constants. K2 is at temperature T2, K1 is at temperature T1 here. Delta H is enthalpy of the reaction, R is gas constant, T1 is temperature T1, T2 is temperature T2. This is the final formula which we get in this case here. Now see how the equilibrium constant changes. If delta H is positive, delta H positive means the reaction is endothermic, forward reaction in this particular case. So if delta H is positive, T2 greater than T1 means you are increasing the temperature. If you increase the temperature T2 greater than T1 and the reaction is endothermic, simple mathematics, K2 will come out to be greater than K1, means new equilibrium constant will be greater than the previous one. Now, if this reaction, as actually this reaction is PCl5 decomposing to give PCl3 and Cl2, this is endothermic reaction in this particular case. T2 greater than T1, so K2 will come out to be greater than K1 because delta H is positive for the forward reaction. We write equilibrium constant for this. Suppose at a temperature T1, equilibrium constant is 5. So we will get 5 equal to PCl3, concentration of PCl3 into concentration of Cl2 upon concentration of PCl5. Okay, this will be the case here. Means this ratio must be equal to 5. Now, we increase temperature. As per this mathematical equation, K2 would have become more than K1. If K2 becomes more than K1, means new equilibrium constant will be more than 5. We assume it to be 10. We simply assume it to be 10. This ratio now obviously should become equal to 10. And to make it equal to 10, what should happen? Numerator should increase while denominator should decrease. Means where the reaction should shift? In forward direction. Got it? This is the mathematical explanation for effect of temperature on chemical equilibrium. Similarly, we can understand if you decrease temperature, why the equilibrium shifts in backward direction. See here, T2 less than T1. If T2 is less than T1 and delta H is positive, T2 less than T1, delta H positive like it is for forward reaction, then K2 will be less than K1. means new equilibrium constant for this expression will come out to be less than 5. You assume it to be 2, means this ratio now should become less than 5. In order to make this less than 5, numerator should decrease, denominator should increase. Means the equilibrium is going to shift in backward direction. Got it? Similar expression we get for physical equilibria also. Physical equilibria. We discussed ice in equilibrium with water. Forward reaction, as everybody knows, is endothermic. So obviously the backward reaction is going to be exothermic. Very simple actually in this case. You increase temperature, ice starts melting to convert into water. Okay, the reaction is, the equilibrium is shifting in that direction where the reaction is endothermic. You decrease temperature, equilibrium shifts in backward direction, water starts converting into ice. Got it? Similarly, if you go for water in equilibrium with vapor equilibrium, this equilibrium we discuss. Again in this reaction, the forward reaction is endothermic. This is endothermic reaction, while the backward reaction is exothermic reaction. Increased temperature, equilibrium shifts in forward direction, water starts converting to vapors. Decreased temperature, vapors start condensing to give water. The reaction shifts, the equilibrium shifts in that direction where the reaction is exothermic. Okay, so this is effect of temperature over physical equilibria as well as chemical equilibria.